wonder how these devices, like your phone, camera, or even the light in your house, store and use energy?
What happens if we change the size of the plates in a capacitor? Or if we add something new between them? Does the energy change? How do these small parts help our technology work? Today, we're going to explore capacitance, the science behind how capacitors store energy, and how small changes can affect their behavior. You'll be surprised to see how something so simple can play such an important role in our everyday gadgets. So, are you ready to learn how these tiny parts work? Let's find out together.
Today, we'll be discussing capacitance and its applications, including how capacitors store energy, how we calculate capacitance, and how capacitors behave in different configurations. We'll also use a PhET simulation to demonstrate these concepts in action. Capacitance is a measure of a capacitor's ability to store charge. It depends on three main factors: the area of the plates, the distance between the plates, and the dielectric material between the plates. The formula for capacitance is capacitance equals epsilon naught times area divided by distance, where C is the capacitance, A is the area of the plates, D is the distance between the plates, and epsilon naught is the permittivity of free space. In simple terms, a larger plate area or smaller plate separation increases the capacitance. Let's take a look at this in the PhET simulation. As you can see in the simulation, increasing the plate area increases the capacitance, while increasing the distance between the plates decreases the capacitance.
Now, let's talk about calculations in capacitance. We use the formula C is equals to Q over V, where Q is the charge on the capacitor, V is the voltage across the capacitor. If we know the capacitance and the voltage, we can now calculate the stored charge. And if we know the charge and the capacitance, we can calculate the voltage. Let's go through an example together. Imagine we have a capacitor that stores a charge of 0.05 coulombs at a voltage of 5 volts. What is its capacitance? A. 0.01 farad, B. 0.25 farad, C. 0.5 farad, D. 1 farad. To calculate the capacitance, we use the formula C is equals to Q over V. Let's plug in the values we know. We have Q, or the charge on the capacitor, is equals to 0.05, V, or the voltage, is equals to 5 volts. So, we have C is equals to 0.05 over 5 volts. Now, let's do the math. So, the correct answer is 0.01 farad. That was simple, right? As you can see, the voltage increases when we increase the charge, or decrease the capacitance. Similarly, increasing the capacitance or decreasing the charge will lower the voltage.
Now, let's focus on parallel plate capacitors. These are one of the most common types of capacitors. A parallel plate capacitor consists of two conductive plates separated by an insulating material called a dielectric. The capacitance depends on the area of the plates, in which larger plates store more charge. Next, the distance between the plates. The closer the plates are, the higher the capacitance. And the third one, the dielectric material. A dielectric increases the capacitance by reducing the electric field between the plates. The formula for the capacitance of a parallel plate capacitor is capacitance equals epsilon naught times area divided by distance. Now let's use the simulation to show how the capacitance changes when we modify the area of the plates and the distance between them. As you can see, when the plate area increases, the capacitance increases. If we increase the distance between the plates, the capacitance decreases. Let's try with an example. A parallel plate capacitor has a capacitance of 2.5 microfarads and is charged to 100 volts. What is the charge stored? A. 0.25 coulombs, B. 0.0025 coulombs, C. 2.5 times 10 to the negative fourth columns, and D. 25 columns. The charge stored in a capacitor is given by the formula Q equals C times V. Substituting the given values, Q equals 2.5 times 10 raised to the power of negative 6 times 100 equals 0.0025 columns. So the correct answer is B, 0.0025 columns. Next, let's explore how capacitors are combined. Capacitors can be connected in series or parallel, and these two connections affect the total capacitance in different ways. First, capacitors in parallel. When capacitors are connected in parallel, their capacitances add up. The total capacitance is C sub EQ equals C1 plus C2 plus C3 and so on. Next, capacitors in series. When capacitors are connected in series, the total capacitance is smaller than the smallest capacitance. The formula for the total capacitance in series is 1 divided by C sub EQ equals 1 divided by C1 plus 1 divided by C2 and so on. Let's use the FET simulation to see how these two configurations work. In this, we're going to use the same value from the single capacitor, series, and parallel capacitors. This is the value of the capacitor, and this is for the battery. The battery has 1.5 volts. This plate has a positive charge, and this plate has a negative charge. The total capacitance of the single capacitor is 0.10 times 10 to the negative 12 farads. This is in series capacitor, with the use of the same value in single capacitor. However, the total capacitance is decreases compared to the single capacitor, and the potential difference of the capacitors are different to the battery. The capacitors have 0.75 volts, and the battery has only 1.5 volts. With the same voltage of the capacitor 2, since they have similar values, which are 1.00 times 10 to the negative 13 farads. How about in parallel? As you can see, the total capacitance in parallel capacitors has increased compared to the single capacitor. In parallel, the potential difference are due to each other because the left plates and upper plates of each capacitor is connected to the positive terminal of the battery by a conducting wire, so that left plate are at the same potential. In the same way as the right plates and lower plates, both connected to the negative terminal of the battery, are at the same potential. This means that the capacitors in parallel have the same potential difference V across them. On the other hand, in series, the potential difference is not similar. However, the magnitude of the charge is the same on all the plates. In short, in series, the total capacitance is decreases compared to the single capacitor, while in parallel, the total capacitance is increasing compared to the single capacitor.
Let's try a problem sample. If two capacitors of 4 mufarads and 6 mufarads are connected in series, the equivalent capacitance is A. 10 mufarads, B. 2.4 mufarads, C. 0.4 mufarads, or D. 3 mufarads. When capacitors are connected in series, the total capacitance is given by 1 over CEQ is equals to 1 over C1 plus 1 over C2. For capacitors of 4 mufarads and 6 mufarads, 1 is equals to CEQ equals 1 over 4 plus 1 over 6 is equals to 3 over 12 plus 2 over 12 is equals to 5 over 12. Therefore, CEQ is equals to 12 over 5 is equals to 2.4 mufarads. So, the correct answer is B, 2.4 mufarads. Number 2. If two capacitors of 4 mufarads and 6 mufarads are connected in parallel, the equivalent capacitance is A. 10 mufarads, B. 2.4 mufarads, C. 0.4 mufarads, or D. 3 mufarads. When capacitors are connected in parallel, the total capacitance is the sum of the individual capacitances. C CEQ is equal to C1 plus C2. For capacitors of 4 mufarads and 6 mufarads, CEQ is equal to 4 mufarads plus 6 mufarads is equal to 10 mufarads. So, the correct answer is A, 10 mufarads.
Now, let's talk about the energy stored in a charged capacitor. The energy stored in a capacitor is given by the formula U equals 1 divided by 2 CV squared, where U is the energy stored, C is the capacitance, and V is the voltage. This formula shows that the energy stored in a capacitor depends on both its capacitance and the square of the voltage. So, if you increase the voltage, the energy stored increases by a factor of 4. Let's try answering the following questions. If the charge on a capacitor is doubled while keeping the capacitance constant, what happens to the voltage? A. It remains the same. B. It doubles. C. It halves. D. It becomes 0. The formula for voltage is V equals Q divided by C. Since the capacitance C is constant, if the charge Q is doubled, the voltage V will also double. So, the correct answer is B. It doubles. Next, what happens to the stored energy in a capacitor if the voltage is doubled? A. It remains unchanged. B. It doubles. C. It quadruples. D. It halves. The formula for stored energy is U equals 1 divided by 2 CV2. Since the energy is proportional to the square of the voltage, if the voltage doubles, the energy increases by a factor of 4. So, the correct answer is C. It quadruples.
Now, let's talk about capacitors with dielectrics. A dielectric is a material inserted between the plates of a capacitor. It increases the capacitance by reducing the effective electric field between the plates. This allows the capacitor to store more charge for the same voltage. The formula for the capacitance of a capacitor with a dielectric is C nu is equal to K times C original, where K is the dielectric constant, which is greater than 1 for most materials. Let's use the PhET simulation to see how inserting a dielectric affects the capacitance. As I insert the dielectric material, I'm going to apply some voltage across here. We are going to take a look at the accumulated charge for the top plate. Now, as I insert, you could see there's a net increase in the positive charges. What happens is that the excess electrons formed by the battery here creates an electric field, thereby repelling the electrons in the dielectric material. Now, as the dielectric material electrons leave or get attracted to the positive plate, it leaves a net positive charge in the dielectric material, thereby having a net increase in charge. Now, no charges cross between the two plates, since this is an insulator. But what happens is that electrons are displaced in the dielectric material by the battery polarities, or the electric battery, which creates an electric field to displace these electrons, hence leaving positive charges. Now, let's take a look at the electric field. So, without the dielectric, we have a net 28 volts per meter crossed between these two plates, which leaves 28 volts per meter. It's total sum, and since there's no dielectric, there's no electric field inside the dielectric. Now, as I insert the dielectric, we see that electric field opposes the one in the plates. So, the electric field in the dielectric material, which is 31 volts per meter, opposes the one of the electric field created by the battery, leaving a net electric field of 28 volts per meter. Notice when I disconnect the battery, it's still 0.284 volts with the dielectric material. But as I remove the dielectric, the voltage across it is increasing, since here we have 60 volts per meter across these two plates. Then as I insert it, the voltage is decreased.